Welcome back to The Explainer. Today, we've got some massively exciting AI news that could fundamentally rewire how large language models process information. Imagine a full orchestra where the strings, the brass, and the percussion are all playing their hearts out, but they're completely ignoring each other because there's no conductor. Honestly, that is exactly how modern AI optimization has been operating. Until now. Today, we're unpacking a brand new paper on a system called TriRoute. It essentially acts as that ultimate symphony conductor for AI optimization, and the efficiency gains here are just fascinating.
All right, let's jump right in. Here is our roadmap. We'll start with the AI efficiency bottleneck, then introduce the TriRoute controller, look at how they prevent routing collapse, peek inside the routing policy, and finally discuss deployment and inference changes. Part 1, the AI efficiency bottleneck, and really why isolated optimizations are failing us.
We all know that compressing LLMs to save on compute is basically priority number one right now. But our go-to methods, they've got a pretty glaring structural flaw. To lower per-token inference costs, engineers rely on conditional computation techniques. The big three are mixture of experts, or MO, which sparsifies the feed-forward network so you're only using a fraction of the parameters. Then there's mixture of depths, MOD, which just aggressively skips entire transformer blocks altogether. And lastly, KV cache quantization, which compresses the attention memory. Now, these are incredibly clever techniques for sure, but traditionally, they are totally isolated from one another.
Look at how isolated routing compares to coupled reality here. These isolated pipelines are essentially wearing blinders. Because they're trained separately, they completely ignore cross-axis dependencies. I mean, think about it. If a highly complex token desperately needs full attention to be understood, it is obviously going to need high-precision cache storage too. But since these systems don't talk to each other, they just optimize in a total vacuum.
So what happens when we optimize in these silos? Well, average performance might look fine, but the rare, difficult edge cases, they just completely break down. We see tail case performance absolutely plummet on complex tasks, things like code generation, arithmetic, and rare named entities. Pure perplexity optimization actually erodes robustness because the routing decisions become totally misaligned with what the model actually needs to compute.
Which brings us to Section 2, introducing the TriRoute controller. Think of it as the ultimate symphony conductor for LLMs.
So, instead of slapping on MO, MOD, and quantization in separate, disjointed pipelines, TriRoute funnels every single token through one single lightweight controller. For every token at every single layer, this controller is making 3 coordinated decisions simultaneously. 1, it picks an attention mode, deciding whether to skip, use local attention, or go with full attention. 2, it selects a sparse set of FFN experts, and really cleverly, this includes a null expert. And 3, it assigns a specific KV cache bit with precision. It treats all of these decisions as a coupled system, putting resources exactly where they matter most.
Now you're probably thinking, wait, doesn't adding a master controller just bog everything down? Actually, check out this number. The TriRoute controller consumes less than 1% of the model's total flops. That overhead is literally negligible. It's totally viable to run this alongside standard transformer inference without crippling your latency at all.
And that tiny overhead unlocks something huge. Normally, standard inference cost is basically just a static side effect of how big your model is. But TriRoute uses what's called a Lagrangian budget constraint. This essentially turns your average compute and memory cost into a controllable dial. It becomes a tunable hyperparameter during training. You can set a strict flops cap and the model organically learns to hit it perfectly. No manual guessing and checking quantization levels required.
Moving on to Section 3, preventing routing collapse, or setting the guardrails for joint training.
Jointly training a coupled system like this is, frankly, super fragile. The big nightmare scenario is something called a cross-axis routing collapse cascade. I know, heavy jargon, but here is what it actually means. If just one axis gets lazy and collapses to a default state, like say it just sends all tokens to the lowest cache precision to easily save budget, the gradient learning signal for the other axes degrades, and a domino effect causes the entire routing system to just fail. To prevent that catastrophic domino effect, the researchers engineered 2 really smart structural fixes, which you can see quoted directly from the paper here. They used per-axis normalization to stabilize the gradient flow, and they introduced a coupling-aware balancing loss. That specific loss function basically forces the controller to play fair, stopping it from over-optimizing one single axis and sacrificing the rest. Under the hood, the math relies on treating the controller as a differentiable policy network. They use heterogeneous relaxation via Gumbel softmax alongside straight-through estimation so those hard categorical decisions don't block the gradient flow. But the true stroke of genius is that fourth bullet point. The null expert actually acts as a hard gate for mixture of depths. So when the controller routes a token to the null expert, it just skips the computation for that layer. It perfectly recovers mod behavior without changing a single thing about the underlying transformer block structure.
All right, Section 4, inside the routing policy and the organic linguistic rules it creates. So what exactly did this controller learn to do? When researchers peeked under the hood post hoc, the patterns were deeply interpretable and linguistically grounded. For complex stuff, sentence initial words, rare subwords, named entities, the controller organically chose to throw heavy compute at them, using full attention and high precision cache. But for highly predictable function words like the or is, it cheaply routed them through lower precision cache and sparse experts. It literally learned the natural bottlenecks of human language on its own.
And the benchmarks back this up entirely. Validated on decoder-only architectures ranging from 160 million all the way to 1.3 billion parameters, TriRoute absolutely Pareto dominates the best independent mod, Mo, and KV quantization combos at matched inference flops. It keeps quality sky-high on complex tokens while aggressively pruning the cost of predictable sequences.
Finally, Section 5, deployment and inference changes, aka the real-world catch.
Because look, it's never just sunshine and perfect benchmarks, right? If you're an engineer looking at this, you're asking the million-dollar question, what actually has to change in your inference pipeline to pull this off? Because this is definitely not a simple plug-and-play API update.
Deploying TriRoute is going to require some serious heavy lifting on your inference server. Since the controller is making discrete per-token decisions on the fly, your KV cache manager absolutely has to support variable bit-width allocation. You're going to need dynamic attention masking. And probably the toughest part, you have to build a custom routing-aware scheduler to batch tokens that have compatible attention modes and cache precisions. If you don't, the branching overhead will completely eat up all those efficiency gains.
So here is the kicker. Theoretical software savings are practically meaningless if your hardware can't keep up. If you don't have blazing fast tensor cores specifically designed for mixed precision cache operations, those massive theoretical memory savings will never translate into actual wall clock speedups. Hardware limitations can, and absolutely will, bottleneck these software optimizations. Which leaves us staring down a massive paradigm shift. We've just seen how a unified controller can act as a maestro, dynamically shifting resources based on the exact linguistic complexity of every single token. So, I'll leave you with this to think about. Will unified routing controllers like TriRoute eventually make our traditional static LLM architectures completely obsolete? It is a thrilling glimpse into the highly dynamic future of AI infrastructure. Thanks so much for joining me on this explainer. Keep learning, and I'll catch you next time.